Hello, and welcome to the next video in my series on basic statistics. And for this video, finite mathematics. The topic in this video is covered in both stats courses and finite math courses. So you may be watching this video in a stats playlist or in a finite math playlist, but either way, it definitely applies to both. Just a reminder, these videos are geared towards individuals who are relatively new to stats, or finite math for that matter, so I'll just be going over the very basics. Now, one different thing about this video is that this video is really about what's going on under the hood. So in previous videos, I've actually worked problems, step by step, very slowly, so you can understand what we're doing. This video is actually sort of what's going on behind the scenes. And more specifically, it's really going to talk about the areas where stats and finite math actually overlap and inform each other. So this is sort of what's going on behind the curtain. But I think it's very interesting, and it helps you understand where this stuff is actually coming from. And finally, if you're watching this video because you're having problems in a course, I want you to stay positive and keep your head up. If you're watching this video, it means you've come pretty far in your education already. And just because you've hit this bump doesn't mean you can't be successful in the future. So, I believe in you, and you should too. So with all that being said, let's go ahead and get started. So this video is the next in our series on basic counting principles, and it's sort of an extension of the idea of combinations. And I call this presentation nearly normal, which I guess would describe me. So we're going to talk about combinations in a different way, and the way we're going to use it is how it begins to inform statistics, sort of the theoretical background of what we commonly think of as statistics. So let's go ahead and get started. So in several prior videos, we discussed counting involving combinations, and we asked how many groups or sets of size R can be chosen from a larger group of size N. So we write this as C parentheses NR, or CNR. And sometimes in stats books it's written a little bit differently with superscripts and subscripts, but it does mean the same thing. Now we say that as N choose R. We have N amount of things or events, and we're going to choose a group that is size R. So for example, we can have 12 things or 12 events, and we're going to select from those 12 groups of 3. And in this case, there are 220 different ways to choose a group or set of 3 out of 12. So N choose R, 12 choose 3, just as an example. In this case, that's 220. So there are 220 unique sets or groups of 3 that can be chosen from a larger group of 12, and that's just basic combinations. So there's our N choose R. Now here are a few things we know. We know that N is our total group size, right? And R is our selection size. So in our previous example, 12 was N, that's our total group size, and R was 3, which was our selection size. Therefore, R, our selection size, can be any natural number between 0 and N. So let me unpack that real quick. First of all, what's a natural number? Well, natural numbers are what we think of as whole numbers beginning at 0 and going up. So 0, 1, 2, 3, 4, 5, 6, and so on. So R can be any natural number between 0 and N. So that should make sense. We can choose 0 from, say, our 12, but we cannot choose more than what we have to choose from. So in the case of 12, we could have 12 choose 12, or 12 choose 0, but we could not have 12 choose 13. Doesn't make any sense, because we can't choose 13 when we only have 12 to choose from. So all that sentence is saying is that R can be any number between 0 and N, any whole number. So in a more formal mathematical terms, we could write it like this. So for our 12 example, we can say C, parentheses 12, that's sort of our combination. And then where R is, that can be anything between 0 and 12. Any whole number between 0 and 12. And that should make sense. So we could have 12 choose 0, 12 choose 1, 12 choose 2, 12 choose 3, and so forth, all the way up to 12 choose 12. So what we're actually doing there, and I don't want to freak you out by saying this, but what we're doing is we're defining a discrete random variable. And what we're saying is that our discrete random variable is R. So another way of thinking about that is that we're just substituting in values of our random variable for R, which in this case are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So if you want to watch previous videos to learn more about what discrete random variables are, go ahead. But all I'm saying is that the value for R can be between 0 and 12, all the whole numbers. That's really all that means. So let's look at the case of choosing from a group of 2. So I'm going to be repeating this chart in later slides, so they'll follow this same pattern. Over on the left we have N, which is 2. So we're choosing from a group of 2. Now on the R column, that's what we can choose as a group size. So we can choose 0 from our 2, we can choose 1 from our total of 2, and we can choose 2 from our total of 2. In the expression, I went ahead and wrote them out as you would write them in your work or whatever. So we have 2 choose 0, 2 choose 1, and 2 choose 2. And if you figure those out, that is 1, 2, and 1. So 2 choose 0 is 1. There's only one way to choose 0 from 2. 2 choose 1, that's 2. So if you think about it, if I had 2 coins, maybe a US quarter and a US nickel, I could choose the quarter if I chose 1, or I could choose the nickel if I chose 1. So there are 2 combinations of choosing 1 there. And then 2 choose 2. Well, if I have 2 things and I choose both of them, there's only one way to do that. So if I have my 2 coins in a bag and I reach in and grab both of them in my hand, well, that's it. There's only one way to do that. They're both in my hand and that's it. So 1, 2, and 1. Now if we plot the frequency of each outcome, so 1, 2, and 1, we have a histogram. That's what a frequency plot is. Now, one example isn't enough, so we'll do another here in a second. But if I plot it, here's what it looks like. So you can see I have 1 on the left, and then 2 in the middle, and then 1 on the end. So that's 2 choose 0, which is our 1, 2 choose 1, which goes up to 2, and then 2 choose 2, which is 1 as well. So all we're doing there is making a histogram of the number of outcomes in our combinations. And that's just for 2. So let's go ahead and do another one. And this is what I call the fabulous 5s. So in this chart, we're selecting from 5. So our N is 5. Our R can be anything from 0 up to 5, and all the whole numbers between. So we can have 0, 1, 2, 3, 4, and 5. So our expressions are 5 choose 0, 5 choose 1, 5 choose 2, etc., all the way up to 5 choose 5. We figure those out, and our combinations are 1, 5, 10, 10, 5, and 1. Now that should sort of pique your interest because those are mirror images of themselves. So 1, 5, and 10, and then 10, 5, and 1. Now if we graph that as a histogram, it looks like this. So you can see on the left we have 5 choose 0, which is one way to do that. 5 choose 1, there's 5 ways to do that. 5 choose 2 is 10. 5 choose 3 is 10. 5 choose 4 is 5. And 5 choose 5 is 1. So if you look at the shape of this histogram, you should begin to see this shape that you've maybe seen before. Okay? So you can see that it has a sort of long section or a hump in the middle. It's symmetrical left to right, and it has two tails along the ends on the left and right. Now let's do this for tens. So now we're choosing from 10. So n is 10, of course, and then our r, which is our group size or our selection size, can be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10. So 0 up to 10, all the whole numbers. Then, of course, that's 10 choose 0, 10 choose 1, 10 choose 2, etc. So we figure those out. We have 110, 45, 120, 210, 252, 210, 120, 45, 10, and 1. So again, it's symmetrical. The only one that doesn't have a mirror is the 10 choose 5. Now, I also want to point something out here. Notice that the 10 choose 5 has the most number of combinations. And that's pretty important in this, because you'll see another example here in a second. So this is sort of another mirror image. And if we graph that, it looks like this. So I didn't put the combinations in here because they would be too small. But on the left-hand side, we'd have 10 choose 0, and then 10 choose 1, 10 choose 2. The long bar in the middle is 10 choose 5. And then we go back down to the right, 10 choose 6, 10 choose 7, etc. Now I'm going to do something a little bit different. Instead of graphing it as a bar graph, as a histogram, I'm going to graph it as a smooth line or a smooth curve. And here's what it looks like. Now again, that shape should begin to look familiar. You have seen this before somewhere. I can almost guarantee it. But we're going to do one more example before we actually talk about what that is. So, the chart on the left is just a histogram, which we often do for discrete random variables. But on the right-hand side, we did it as a smooth curve. Now, we usually would not use a smooth curve for a discrete random variable like this, but I'm trying to show you how eventually they kind of become one. So let's do one more example. So here is 20. So now we're going to do a group size of 20. So 20 choose 0, 20 choose 1, 20 choose 2, etc. I'm not going to put all those combinations on the slide because they're just too many. You won't be able to read them. But here's a graph of it. So this is a graph of our combinations of 20. From 20 choose 0 up to 20 choose 20. And that's our histogram. So you can see there in the middle, we have an outcome, which is 20 choose 11, I believe, that has over 180,000 combinations. It's pretty crazy, isn't it? So there in the middle, we have over 180,000 combinations, and then it tails off symmetrically on the sides. Now, if I graph this as a smooth curve, that's what we get. Now, that shape should begin to be obvious. What is it? Well, a lot of us know it as the bell curve. And those of us that do stats and things like that would call it the normal curve. So, the curve on the right is an approximation of the histogram on the left. And if I walked you through the choices of 2, the choices of 5, the choices of 10, and the choices of 20, the curve on the right becomes more and more like a normal curve would look. So again, this is where I'm talking about how finite math and stats overlap and inform each other, because, well, this is where they actually do. Okay? So let's go ahead and continue. Now I went ahead and made the 20 is plenty histogram here in the middle so you can see it nice and big. And now I'm going to superimpose the curve on top of it. And there it is. So you can see that the histogram and the curve that sort of outlines that histogram are almost a perfect match. Now, of course, the difference is that the histogram is a pure discrete random variable. And remember what we mean by discrete. That means that each one of those bars represents a specific number. So each bar is, say, 20 choose 5, or 20 choose 10, or 20 choose 14, or whatever. And then the smooth curve is an approximation of that histogram. Okay? But they're both based on the exact same data. So the histogram and the curve are based on the exact same information. The blue, the smooth, is just an approximation of the actual histogram. Okay, well, so what? Okay, why is this important? Why are you showing me what sort of is happening under the hood with respect to combinations and normal curves and stuff like that? And that's because we're now entering the arena in which finite math and stats overlap and inform each other. So you can take an introductory stats book and a finite math book that a freshman would use, and you could section off chapters that are in both books. And this is one example of that. Now, what does this mean as far as understanding? As we increase our group size, like we did here, so we went from 2 to 5 to 10 to 20, and then calculate the frequency of each possible combination. And again, our R just goes from 0 up to our group size. So we can go from 20, choose 0, to 20, choose 20. Our histogram begins to look a lot like a normal curve, or what we commonly call a bell curve. As our group size increases, and we plot the frequency of each outcome, each combination, it begins to look a lot more like a normal curve or bell curve. This is not an accident. What we think of as the normal curve is actually a derivation or byproduct of counting and its associated probabilities. And it's counting and probabilities sort of taken to their extremes. Okay? So when I say that the normal curve is actually a derivation or a byproduct of counting and its probabilities, what I'm kind of saying, and what I am saying, is that the histogram is for discrete random variables, and the smooth curve is for continuous random variables. But we can use the discrete random variables, like the size of the group that we're choosing from our total, to approximate our continuous smooth curve or normal curve. So we use the discrete to approximate the continuous. So think of what our histogram would look like if we increased our overall group size towards infinity. So in this case, we did 5, 2, 5, 10, and 20. Well, what if we did 100? And we went all the way from 100, choose 0, all the way up to 100, choose 100. And then we graphed that histogram, or even a bigger number. Let's say 10,000. We went from 10,000, choose 0, all the way up to 10,000, choose 10,000. And if we increase that number towards infinity, we are getting close, well, we basically are coming close to the normal curve. So the leap from discrete random variables and these histograms and continuous random variables is basically calculus. Now, you don't need to know that to go, to do what we're doing, but if you've had calculus before, you know that one of the basic fundamental things about calculus is dealing with things that approach infinity. So these bars in our histogram get squished together. There are so many of them. So many, and eventually they become so numerous that they are almost indistinguishable. They are almost invisible. And that creates a normal curve, this solid area under the curve. Okay? So just think as the normal curve as a discrete random variable histogram taken towards infinity. So group sizes towards infinity. And of course, this is where we make the jump from discrete random variables like, 50 choose 26 to continuous random variables. We're going to talk more about those in future videos. So we go from a histogram in the discrete world to a continuous function in the continuous world. Now, I know this is a lot, and this slide's probably the hardest to sort of wrap your head around if you're not familiar with, calculus to some extent, which you don't need to know to do this at all. But you just have to think that what we're doing here is we're taking something we already know how to do, and that is combinations. 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, and 5 choose 5. And then we take that and blow it up towards infinity. So like a million choose 0, all the way up to a million choose 1 million. Okay, that's crazy. It'd be hard to even write numbers that big. But that's all we're doing. We're taking something familiar and running with it towards infinity. And then once we get closer to infinity, we get towards a continuous curve, or the continuous normal curve, or continuous function. Because a lot of stats is based on continuous data and continuous curves and things like that. So I want you to understand actually where it comes from. It just doesn't fall from the sky. Okay, so that wraps up our look under the hood of what's going on in the overlap between finite math and stats. If we take a basic component of, say, finite math, because it tends to be a bigger part of finite math, like combinations, and we take simple combination problems and then we extend them far towards infinity in terms of their size, we end up in some of the fundamental areas of statistics. Okay, so I want you to see how they're tied together and what we're actually talking about when we talk about probabilities and statistics. Okay, so in another video we'll actually do some of these very same charts, but then we'll talk about probabilities. And once we talk about probabilities, that gets us even closer to the fundamental ideas in statistics. So, I'm going to be quite honest with you right here. Learning a bunch of formulas and plugging a bunch of numbers into them mindlessly is not learning stats. It's not learning finite math. If you don't understand exactly what you're doing and why and where it's coming from, you're just regurgitating a bunch of crap from your classes or whatever else. If you really want to understand what's going on, you have to understand things like this. Okay, that's my soapbox moment. Just a reminder, if you're having problems in a course, I want you to hang in there, stay tough, keep your chin up. With a little bit of hard work and patience, you can get through it. I believe in you, and so should you. So if you like this video, please give it a thumbs up, share it with classmates if you think it was helpful. If you don't, leave a constructive comment, and I'll try to improve it the next time I do them. So all that being said, let's go ahead and wrap up. Thank you very much for watching, and I look forward to seeing you again next time.